Independency and conditional independence. Independence. We say that an event alpha is independent of an event beta in P, denoted as P is alpha is independent of beta if P of alpha given beta equal to P of alpha, or if P of beta equal to 0. So they are saying that P of alpha given beta should be equal to P of alpha, and your P of alpha or P of alpha given beta equal to P of alpha into P of beta. So a distribution P satisfies A alpha is independent of beta if and only if P of alpha intersection beta equal to P of alpha into P of beta. So your proof is given to you. We'll check the example. Suppose that we toss two coins. A is the first toss results in a head. Beta is the second toss results in a head. These two events are independent. Learning that beta is true would not change the probability of alpha. Consider the event A. The die outcome is even. Beta, the die outcome is 1 or 2. Each of the 6 possible outcomes has a probability 1 by 6. Then these two events are independent. So the die outcome is even, the die outcome is 1 or 2. What is the probability? Probability is 1 by 6. So we say that the events are independent events. Conditional independence. A more common situation is when two events are independent given an additional event. So two events, they are independent given a additional event. Example, chance to get accepted to graduate studies at Stanford or MIT. Stanford admitted to Stanford, MIT admitted to MIT. Not independent. Admitted to MIT increases the probability of being admitted to Stanford increases the probability of being admitted to MIT. So they are not independent, because what is it saying? Statement is saying that if you are admitted to Stanford, then your probability increases to get admitted to MIT. Consider university accept based on the student's grade points, that is a GPA. Our student has a GPA of A. Conditionally independent. P of MIT Stanford, grade A is equal to P of MIT given grade A. Now in this case we say MIT is conditionally independent of Stanford given grade A. So it is conditionally independent of Stanford given that the student has got a grade A. So it is not actually independent. If you are getting admission in Stanford, that means your chances are increasing to get in MIT. But if the university MIT is taking this GPA, then it says that you will get admission into MIT if you have got a grade A. So it is conditionally independent of Stanford given. What is the condition? Condition is get a grade A, get into MIT. Then you are independent of Stanford condition. So otherwise what is it saying? That if you are admitted to Stanford, you are admitted to MIT. The probability increases. So getting into MIT is independent to getting into Stanford. Now what conditional independence means? Adding a event to make the two events independent. So to make Stanford independent of MIT, I am adding an additional event. This additional event is grade A. If you get a grade A, then whether or not you are admitted to Stanford, irrespective of getting admitted to Stanford, you will be getting admitted to MIT. So if you get a grade A, you get admitted to MIT. So irrespective of getting admitted to Stanford, you will get admitted to MIT if you get grade A. If you are not getting a grade A, then you have to get admitted to Stanford, then only your chances will increase to get admitted to the MIT. So they were not independent previously, but then what did I do? I added a condition of grade A. If you are getting a grade A, then no need to get admitted in Stanford. So they became conditionally independent. On adding a condition of grade A, they are becoming independent events. Before the condition was not added, they were dependent. MIT was dependent on Stanford. As soon as I added the condition of grade A, MIT became independent of getting admitted to Stanford. So we say that an event alpha is conditionally independent of an event beta given event gamma in P, denoted as alpha is independent of beta given there is an event gamma. If P of A given alpha given beta intersection gamma equal to P of alpha given gamma or P of beta intersection gamma is 0. So there what we were saying, P of, in independent events we said P of A given B is equal to P of A. We said that this is the condition. Or P of A given B was P of A into P of B. But what did we say? We said that beta is equal to 0. So here we are saying that the intersection of beta with gamma is 0. Independence of random variables. Until now we have focused on independence between events. Thus we say that two events such as one toss landing heads and a second also landing heads are independent. However, we would like to say that any pair of outcomes of coin tosses is independent. To capture such statements, we can examine the generalization of independence to a set of random variables. So let x, y, z be a set of random variables. We say that x is conditionally independent of y given z is a distribution in P. If P satisfies the condition for all values, x belongs to val of x. So the P should satisfy the condition that x equal to small x is independent of capital Y equal to small y, given that there is an additional condition z equal to, this is what? This is your additional event. The variables in the set Z are often said to be observed. If the set Z is empty, then instead of writing x is independent of y such that null, we write x is independent of y. We say x and y are marginally independent. So if your Z, that means the added event is empty. The event which you have added is empty, then we say that x is independent of y. Querying a distribution. Our focus is on using a joint probability distribution over multiple random variables to answer queries of interest. Query type, probability queries. Given evidence, the values of a subset of random variables, compute distribution of another subset of random variables. Map queries, maximum a posteriori probability, also called as most probable explanation. What is the most likely setting of a subset of random variables? Marginal map queries when some variables are known. So this is a student Bayesian network. So in the student Bayesian network represents a joint probability distribution over multiple variables. Bayesian network represent them in terms of graphs and conditional probability distributions, resulting in great savings in the number of parameters needed. Probability queries. Probability queries are nothing but given evidence, the value of subset of random variables, complete distribution of another subset of random variables. So this is the way probability query is represented. This is again the most probable explanation. All this will come in the later modules. Then example of map queries, that is medical diagnosis problem. So there is a medical diagnosis problem given to you and you need to figure out which is the most likely disease, which most likely diseases and symptoms, most likely symptoms. All this you figure out with the help of a Bayesian network modeler. So this is there. Next, Again, this is marginal map queries. Example of marginal map queries.